Good morning everyone, I am Strish. I hope everyone's doing well. Here in this video, organic chemistry video, we're looking at this DDT. You've heard of it. It's a insecticide, pesticide, which was, I believe, invented in 1890s. And then it was utilized in the 1940s up to the 1970s. Then it was phased out because of its environmental impact. Anyhow, this insecticide works, or it used to work, by affecting the sodium channels in the neurons of insects and or pests. Therefore, keeping those sodium channels open, the nerve or the neuron was continuously activated, leading to spasms and eventual death. What is DDT? Dichloro diphenyl trichloroethane. Now look, start right here. Trichloroethane. I have here a ethane compound, C and a C, two carbons. That's ethane. In one carbon, I have three chlorines, so that's trichloroethane, which is this part right here. Then I have dichloro. These are the two chlorines here at the end attached to the diphenyl, which is this part you see, these two phenyl groups or benzene groups. Dichloro, diphenyl, trichloroethane, and that's DDT. Now, how do you go about synthesizing this compound? Now consider what you have over here. You have a benzene with chlorine. You have a compound over here, and I'm looking particularly, let's erase this at this part right here. I have a compound here, a chlorobenzene, which is a ortho-para director. Therefore, it will be the item which will lead everything else. Electrophilic aromatic substitution. Think about your benzene as C6H6, which it is, and you look at it and you draw it out like this. When you draw it out like this, you have your three double bonds. But because of hybridization, each of these carbons is sp2 hybridized, is what it is. It's not sp3, sp2. Every single carbon over here is sp2 hybridized because those double bonds are in essence affecting everything. A resonance structure can be developed. As you can see, it would be this right over here, where the carbon double bonds are alternating with the other carbons. You see the difference between the two, but this right here represents the better representation of this, because it shows that the double bonds are affecting in essence all the six carbons. Each of these carbons is sp2 hybridized. If you look at it, a single carbon over here, you have a pi electron either here or here, but you have a pi orbital. It looks like a dumbbell. That's what it looks like. But each of these carbons will have a pi orbital, and then in that pi orbital you can find yourself an electron. That electron will generate a pi electron cloud. If you were to flatten this benzene and make it just look like a sandwich, here's my benzene, and I'm putting here a B for benzene. I have here a pi electron cloud above and a pi electron cloud below. You can either have electrons here, you can have electrons here, but these are your pi electrons. Those pi electrons enable benzene to act as a nucleophile. Now, if you have something which is a compound but it's an electrophile, it has been activated, this electron can come over here and attack it, or you can say the electrophile is attacking the benzene. Either way, how you say it, it doesn't really matter. Then you can attach your benzene, here's your benzene, and you've attached the electrophile. But this electrophile had to be activated first. Without activating, this reaction couldn't occur. How would you have activated this? You would have started here with the compound, which is just your E, and you would have, in the presence of acid, activated it. The compound, what would be your electrophile, is activated by your hydrogen ion from your acid and making it into an electrophile. The benzene acts as a nucleophile and it attacks that, and you attach the electrophile on the benzene. This right here is your electrophilic aromatic substitution, which is how this compound is going to come about. Considering all of this, let's look at the synthesis. We will look at the synthesis in stages. I'm looking here at trichloroacetaldehyde because it is an aldehyde. You have a carbonyl with hydrogen, trichloroacetaldehyde. This here represents what I was alluding to before, my E. In the presence of sulfuric acid, which is my hydrogen ion donor, you know, strong acids, nitric acid, sulfuric acid, HCl. Let's just use HCl. When you ionize them, you have this hydrogen, the proton, and a conjugate base. Similarly, when you do this, H2SO4, you have a first acid dissociation constant, your Ka1, which is very good because it can easily donate that. But the second acid constant is not good. It's not going to likely donate it easily. But this is what you have. You're looking for this right over here, this proton. Anyhow, in the presence of a strong acid, you will activate this. But how will you activate it? Consider this right here as being nothing other than, now I'm putting here a proton because that's what I'm really looking for. You have an oxygen here with the ability to act as a Lewis base, an electron pair donor. It can attack that. And what do I have? I'm going to abbreviate here. My trichlorine, my carbon, and then I have this. This is what I've generated, an activated E. Here's my E, my activated E, but it's not really fully ready yet. You have a double bond here. You know this is my double bond, but each of this is representing a bunch of electrons. Each of these represents a single bond. One of these can go over here and fill the charge deficiency. As you can see, you can have a shifting of electrons. When you do that, you'll have your this item develop. You will have brought in your 2 electrons. You had 4 electrons, but 2 of these electrons were lost in the development of the oxygen-hydrogen bond, but you regenerated them by getting rid of your double bond, making it into a single bond, and now your positive charges come over here, and this right here is my electrophile. We'll call it E positive. That E positive or my electrophile is what will be attacked by the benzene ring. So now keep this aside. You have this over here, and we have it. Now what we will do is bring in what we have, a chlorobenzene. But let's start here with benzene, and we attack it in the presence of diatomic chlorine and a Lewis acid, FeCl3, and we'll generate our chlorobenzene, which here is a ortho para director. The circle in the benzene ring is a way of representing exactly this, and you represent it like that. Because of resonance structures, those double bonds could have been on other carbons, as you can see like this. These 2 are resonance structures, but you represent it like that in a more unified manner, hence I'm utilizing that. This right here is your nucleophile, this right here is your electrophile. It's going to attack that. But you know this right here is ortho para director. It could attack over here and it could attack here. Here's your ortho position, here's your para position. Simply because of steric hindrance, you're more likely to get the para, though you will get the ortho. When you're doing the DDT synthesis, you'll get both. You'll have the ortho compound, you'll have the para compound, but you'll isolate the ortho and get rid of it, and you'll focus only on the para compound, which is what we're doing. We're going to do a para attack over here. The one double bond, because if you look at it like this, it's looking something like this. I have a double bond here. This one double bond will attack that electrophile, and you will add it here in the para position. This is just for exemplification purposes, but you can picture this in your mind. You're attacking it over here. So let's bring it in. I've done my electrophilic attack over here. What will my end result be? I'll have my chlorine, and I'll have this benzene, chlorobenzene, which is a phenyl group with a chlorine attached to it. Then I'll have this CH, my trichloro part, and my OH. This is where I am right now, but you see how I'm kind of running out of space. We've seen how starting from trichloroacetaldehyde, we've activated in the presence of acid and we've generated our electrophile, but we've used the electrophile. Keep in mind everything here is being synthesized in an acidic environment. You always have to remember that. So let's generate some space by erasing everything else. You've seen it. You can always rewind and see it again. When you come here at this stage right here, you have a neutral compound. But if you picture the fact that you're still here in an acidic environment, which you are because we had sulfuric acid coming into play, this right here can act again as a Lewis base. It can attack a hydrogen ion, and then just focusing only on this part, what you would have is you would have your trichloro part, and you'll have here an OH2 positive. You've converted this OH into an OH2, a water molecule. This water molecule can dissociate. When it dissociates, what do you have? Well, let's bring it in. We have our chlorine, we have our benzene, and then we have our C hydrogen, then we have our carbon here, and then the trichlorine. Remember, this right is my ethane group. Here's my hydrogen. Here I've developed a electrophile yet again, because this hydroxyl got protonated, became a water molecule. The water molecule drove off and we've generated an electrophile, and you've seen it come into play. What do you think must happen now? We have an electrophile here. Another nucleophile must come into play. What is that other nucleophile? Another chlorobenzene. Now the double bond, I'm just showing you a representative double bond, will attack over here. Of course I have this circle representation representing the unified resonance structure, but this is going to attack over here again in a para direction. Because of steric hindrance, it will prefer that. When you do that, you'll have your end result form. You'll have your chlorobenzene form here, you have your carbon, you have your hydrogen, you have your other benzene and the chlorine, and then here you'll have your this item right here, your trichloromethane group. CCl3, and here's your end result, and it has been synthesized. It is nothing other than a glorified electrophilic aromatic substitution reaction. That's what it is. You've had to use a chlorobenzene, a activated electrophile. I showed you how it became activated in the presence of sulfuric acid, which reactivates and generates a second round of substitution reaction, and electrophilic substitution reaction, and you go to your desired end result. Now if you think back to everything, we started here with this compound, trichloro and acetaldehyde. Now you could think, how can we even come up to that? Our synthesis here is complete. This right here is our end product. We've synthesized it. How could you even come up with this compound? Well, you could picture yourself here again with the precursor compound, which would be a CH2OH, an alcohol with the carbon and your trichlorines, your 3 chlorines. And you've done a mild oxidation reaction. The hydroxyl with this part, methyl hydroxyl group, has been converted into an aldehyde. You can picture that happening. So that's how it comes through, by some form of chromium compound. A mild oxidation reaction converts an alcohol into aldehyde. Not a strong oxidation, because it'll take it to an acid, like a trichloroacetic acid. We don't want that. We want trichloroacetaldehyde. But how could this have come about? Well, you could picture yourself starting here with the ethanol, CH3CH2OH. Then you're adding these chlorine by means of radical reactions, free radical reactions, and you've added, in place of these 3 hydrogens, you've added 3 chlorine. So this is how you can synthesize that. And I've shown you how you synthesize your chlorobenzene, a benzene with a Cl2 diatomic Lewis acid FeCl3, you get your chlorobenzene. You do your glorified electrophilic aromatic substitution reactions or attacks using this compound and activating it by means of acid, then obviously your 2 chlorobenzenes, and you come up to your DDT, dichloro diphenyl trichloroethane. Ethane is coming from right over here. And that right there is the end of this video. Thank you for watching.